Now let's see experiment number 3, measurement of viscosity average molecular weight of polymer. So if you recall, we have already done this in third semester, in theory, to measure the viscosity average molecular weight of a given polymer sample using Ostwald viscometer. Apparatus: you need a Ostwald viscometer. It is available in a laboratory: beaker, measuring cylinder, funnel, weighing balance, glass rod, etc. Polyvinyl alcohol, distilled water in chemicals. This is the Ostwald viscometer. This is how it looks like. You have to pump, you have to suck air from this side, and this solution of PVA rises to this meniscus, and you have to just make a marking here and one marking here, and the amount of time it takes to pass from this point to this point, you just have to note it down. Okay. Viscometry is a useful technique for determining the polymer molecular weight. The molecular obtained by this technique is viscosity average molecular weight. Okay, MV. This method is used to determine dilute solution viscosity less than 5%. So you need a dilute solution, okay, for all polymers that dissolve completely without chemical reaction or degradation to form solutions that are stable with time and temperature between ambient and approximately 150 degrees Celsius. The viscosity of a dilute polymer solution depends upon several factors, mainly nature, concentration, molecular weight of polymer, temperature, and shear rate. The viscosity of a polymer solution is considerably high compared to that of pure solvent. Obviously, if you take a pure solvent like water or something, then the viscosity of polymer will be quite high as compared to the increase in viscosity imparted by the macromolecules in solution is a direct function of hydrodynamic volume and hence the molecular weight of the macromolecule. So from this we have concluded to a relationship. The relationship between viscosity of a polymer solution and molecular weight is given by the famous Mark-Houwenk equation, where N is the intrinsic viscosity, M is the molecular weight of the polymer, K is the constant, and A is also the constant for a particular polymer solvent temperature. Okay. System. Intrinsic viscosity can be measured using method of viscometry. Assume that a liquid is flowing through a capillary tube. The time required for the liquid volume V to pass through the capillary of radius R and length L is related to absolute viscosity by famous Poiseuille equation as follows. Poiseuille equals to 3.14 P R raised to the power 4T upon 8 Vi, where P is the pressure head under which the liquid force takes place. On comparing the viscosities of the polymer sample and pure solvent, we get this N by N0. N is the viscosity of the polymer sample, N0 is the viscosity of pure solvent, is equals to T by T0. Okay, where N0 and T0 are the viscosity of and time of pure solvent respectively. The term N by N0 is known as relative viscosity. The other terms related to the measurement of viscosity given below. So all these formulas you need to know: relative viscosity, specific viscosity, reduced viscosity, inherent viscosity, intrinsic viscosity. So as I said, relative viscosity is N by N0, which is nothing but T by T0. Okay. Specific viscosity is N minus N0 upon N0, that is T minus T0 upon T0. Therefore equals to NR minus 1, because relative viscosity T by T0 minus 1 equals to specific viscosity NSP. Now reduced viscosity NSP upon concentration, so that is reduced viscosity. Inherent viscosity, thus just a ln of reduced viscosity. Add ln to it, so NR by C ln you give you inherent viscosity. Now intrinsic viscosity, specific viscosity upon concentration, where concentration tends to 0, that is intrinsic viscosity. Now intrinsic viscosity is also known as Schrodinger index or limiting viscosity number, as specific viscosity is by definition a dimensionless quantity. The intrinsic viscosity as a reciprocal of the concentration in this dimension as a dimension. Okay, so specific viscosity is a dimensionless quantity. Okay, but the intrinsic viscosity has a reciprocal of concentration as its dimension. On solving the equation for intrinsic and reduced viscosity, we have this. Intrinsic viscosity is equal to under root of reduced viscosity minus inherent viscosity upon 0.5 C. into C. Okay, so see, don't get confused between this. I and H is inherent viscosity and I and T is intrinsic viscosity. Okay, to determine the intrinsic viscosity of a polymer from dilute solution, viscosity data, the reduced and inherent viscosity of the solution of various concentration are determined at constant temperature. So इंट्रिंसिक विस्कोसिटी निकालने के लिए पहले तुमको रिड्यूस और इनहेरेंट विस्कोसिटी निकालना पड़ेगा. So what you're going to do, you're going to carry out the following procedure. So and once you get the intrinsic viscosity, then you apply it in the formula, which is given as, this is intrinsic viscosity is equals to kMa. Therefore m is the molecular weight, so it goes like this. The value of A, the constant is 0.64 and K is 45.3 into 10 to the power minus 3. As soon as you get this value, then you can get the value of m, and once you get the value of m, you get the molecular weight. Okay, so that's why we have to calculate intrinsic viscosity. So let us see first. But how will you calculate intrinsic viscosity? By knowing T and T0. Okay, so the polyvinyl alcohol sample is prepared by dissolving 1 gram of polymer sample in 100 ml of water. So take polyvinyl alcohol 1 gram and dissolve it in 100 ml of water. The prepared polymer solution and the viscometer are maintained at constant temperature. The solution is transferred into the viscometer. The liquid level in the viscometer is brought above the upper graduation mark by means of air pressure. Like I said, from one mark to another mark, the time is started exactly when the liquid meniscus passes the upper graduation mark and stopped exactly when the meniscus passes the lower graduation mark. The procedure is repeated at least 3 times for solution of different concentration of pure solvent. The time required for liquid to pass through the graduation mark is called efflux time. The graph of the reduced viscosity versus concentration is plotted. The relative viscosity, specific viscosity, reduced viscosity, inherent viscosity, intrinsic viscosity are to be determined. So you take all these samples, and for sample number 1 you will take water because it will give you the value of T0. So first from the upper meniscus to lower meniscus, whatever time is there, then again do the same procedure, then again do it, so that you get a average. You just can't take one reading and go ahead, so you have to take a average time. So once you get it of water, then take it for 0.5% polyvinyl alcohol solution, then also take it for 0.1% polyvinyl alcohol solution. Okay, so 3 readings you will get. Then using Ostwald viscometer we can identify the molecular weight of the polymer. So suppose you get the value of the intrinsic viscosity by using all those formula, then simply substitute the intrinsic viscosity in this formula, and the value of K and M I am giving you. A is 0.64 and K is 45.3 into 10 to the power 3, and just simply substituting it, you will get the viscosity average molecular weight of polyvinyl alcohol. So since you have been taking it for 3 different readings, so you will get 3 values of viscosity average molecular weight of PBA, and then simply take their average, so you will get the final viscosity average molecular weight. So the RHS of this experiment I will be giving you in the notes. Just go through it, you will get clear cut idea how to perform this experiment. It is very simple. You just have to make the solution of polyvinyl alcohol, okay, and then from this mark to this mark, how much time it takes to pass, you just have to note it down. Very simple experiment, but some formulas are there which you need to know. Now they study the resilience testing method to measure percent rebound. Okay, the resilience of a rubber compound is a measurement of how elastic it is when exposed to various stresses. Measurement of a material resilience can assist engineers and scientists with choosing the right material for a given application. So most people don't even know what is the meaning of the word resilience. Okay, so resilience is nothing but resilience is nothing but someone or something that bounce back into shape or recovers quickly. Okay, so resilience is the ratio of energy released in deformation recovery to the energy that caused the deformation. Okay, so one test method is the Bay-Shore resilience method. It calls for the dropping of a weighted ball from a specified height onto a given material sample. The rebound height of the ball is then measured and used to determine how resilient the material is to the stress. The result is an indicator of hysteretic energy loss. The percent rebound is measured in the test is inversely proportional to the hysteretic loss. So it's very simple. You take this equipment, okay, and here you place the rubber sample. This is a metal ball. You take it up and just drop it, and you, as soon as you drop it, because this is rubber, it will bounce back. And how long it bounce back, you just measure that. Nowadays slow-mo cameras are available in the mobile phones, so you can know exact height to which it has rebounded. Level the instrument and raise the plunger to the top of its guide rod. Position the resilience scale so that its full mass rests upon the specimen. Lock it in this position. Now I took the plunger up. Release the plunger, then I release the plunger, ensuring that it slides freely on the vertical rod, and note down the rebound height. Lateral force or impact on the guide rod may result in hindrance of the descent of the plunger. Always keep a standard test specimen under the stabilizer when not in use to avoid damage to the plunger. Test 3 specimens from the same sample, making 6 test determination on each specimen. So what he's saying is that you take 3 specimen. So suppose you are testing SBR, styrene butadiene rubber, so take 3 samples of it. Okay, sorry, if you taking 3 specimens, then you have to take 1 styrene butadiene rubber, 1 PU foam and 1 PS foam. Okay, so 3 specimens are there, and you have to making 6 test determination on each sample. So 6 test determination on each sample, or you can do 3 also. Okay, so he's saying 6, but we will do 3 because 3 is given here, and then take the average. Okay, so nothing but resilience is calculated by this formula. Percentage resilience equals to rebound height upon original height into 100, and in this case the original height is 40. Okay, and whatever rebound you get, simply put it in the numerator upon 40 and into 100. So we will take the average reading, of course, in the numerator. Significance and uses. Resilience is a function of both dynamic modulus and inherent friction of a rubber. It is very sensitive to temperature change and to depth of penetration of the plunger. Consequently, resilience values from one type of rebound instrument may not in general be predicted from results on another type of rebound instrument. This test method is used for development and comparison of material. It may not directly relate to end user performance. Conclusion. Testing shows that this tester is very useful for testing of rubber elasticity. This machine is portable and cost effective. It required low maintenance and is easy to handle. You can see it is very easy to handle. The determination of rebound resilience is accomplished by falling a plunger of a specific mass and geometry from a predetermined height to the surface of a test specimen and measuring the distance the plunger rebounds after contact and calculating the ratio of rebound distance to the distance traveled by the mass prior to contacting the test specimen. The ratio is expressed as percentage, and since the scale is graduated into 100 equal divisions, the ratio percentage may be read directly from the scale when the plunger rebounds to its maximum height. Result: the vertical rebound resilience testing method is studied. So now we have done our two experiments. Study the RHS also, which I'll be giving in the Moodle. Thank you.